Welcome everyone. In this session, we'll see how we can work with imagery using ArcGIS API for Python. First of all, let me introduce us to you. I am Ria Jackson and I work as a software development engineer for the core Raster team at Esri Sharjah R&D Center. We also have Shivani Pathak and Kriti Chandran joining with us today. Shivani Pathak works as the product engineer for data science team at Esri R&D Center, New Delhi, and Kriti Chandran works as the product engineer for core Raster team at Esri R&D Center, Sharjah. In this talk, we will introduce you to the WebGIS architecture and will give you a brief overview of what is required to perform raster analysis. Then we'll talk about the raster module in ArcGIS API for Python in detail, and each part of the module would be explained using demos. And then we'll conclude. So now let us talk about the imagery and raster analysis on the web. We will first see what all are needed to perform raster analysis on the WebGIS. To perform the analysis on the WebGIS, you will need an ArcGIS Enterprise. The ArcGIS Enterprise is a collection of different applications working together. These applications include ArcGIS Portal, ArcGIS Server, ArcGIS Data Store, and ArcGIS Web Adapter. We can have different types of server roles assigned to the ArcGIS server, such as the image server, geoanalytics server, notebook server, etc. For performing raster analysis, we'll need the ArcGIS image server federated to the ArcGIS Enterprise. The ArcGIS Enterprise supports different client applications like ArcGIS Pro, web-based applications like MapViewer. We can use the ArcGIS Enterprise through APIs like REST API, ArcGIS API for Python, and in this talk, we'll be using ArcGIS API for Python to perform raster analysis using Enterprise. Now, let us look at the raster module in more detail. An important class in the raster module is the Imagery layer class. It represents the raster published as image services. It has properties to get more information about the dataset and methods to perform different operations on the image services. There are few manager classes that will help you to perform content management, like the Imagery layer cache manager, raster manager, imagery tile manager. Then we have the raster class. Raster objects can represent web-based image services, data store rasters, and local raster datasets. That is, it can be considered as a unified API to work with your raster data, either be it on the web or local to your machine. We have the raster collection class that helps you to create a collection of raster objects and perform operations like map, reduce, filter, and other methods that prepares a collection for further analysis. We have raster catalog item that represents single catalog item of an image service. Shown here in purple are submodules within the raster module. These submodules each contain numerous functions that allow you to perform analysis on your raster. You can perform both on-the-fly computation for visualization as well as distributed computation for persistent data products. Now, Shivani will give you an introduction about the imagery layer class, different functions that are available in the raster module to perform raster analysis, etc.
Now that you are familiar with ArcGIS raster module, let's talk about raster analysis. We can say the ArcGIS ecosystem has 5 core imagery capabilities. First is content. We need data for analysis. ArcGIS supports all major sensor types, including Landsat, Sentinel, and supports microwave and weather data. So you can import data with necessary information and interpret and analyze data properly. After getting data, next step is to visualize and explore it. In ArcGIS, we have tools for different case studies. For example, you need spectral profiles for data with high spectral resolution, time or elevation sliders for multidimensional rasters. After that, you want to analyze the data for creating new information. You can create indexes, perform image segmentation, classification, and now you can also do object detection, instance, and semantic segmentations using deep learning capability. After analysis, next step is map production. Through maps, you can show findings of your analysis. We have different capabilities to create different kinds of maps such as orthophotos, DEM surfaces, etc. Once you are done with map production, final step is management and dissemination. We have fast capabilities to manage, distribute, and share data through web services. ArcGIS has all the necessary capabilities which are required to work with rasters. Raster functions have dynamic rasters and persisted rasters. Dynamic rasters or on-the-fly processed rasters. In the case of on-the-fly processed raster, processing is not permanently applied to the data. Instead, it is applied on the fly as the imagery and rasters are accessed. Functions are chained together to create complex model. In this function chain, you can see how two Landsat multispectral imageries were used for band mathematics, and a raster function remap and color map is applied dynamically. Another type of output of raster functions can be persisted raster. Raster analysis can be used to generate a raster information product by applying the same raster function across the extent of an image service on the portal using save method. The raster function is applied at source resolution and creates a persistent raster product when image gets saved. The ArcGIS.raster.analytics module contains functions that enable you to call raster analysis tools in your GIS and create persisted outputs. Let's see different kinds of raster functions. We have functions related to math like divide, float, int minus, etc. We have functions related to image correction like speckle filtering, functions related to Sentinel-1 correction like Sentinel-1 thermal noise removal, S1 radiometric calibration. We have functions related to data management and conversion like rasterize features, color map for changing symbology, remap for reclassification, spectral conversion, mask, reproject, etc. We have functions related to overlay analysis like weighted overlay, weighted sum. Functions related to visualization and appearance are also present like contrast brightness, pen sharpen, resample. Functions related to surface generation and analysis like aspect, curvature, hill shade, contour. Interpolation functions are also present in the module like interpolate irregular data, swath. You can do analysis related to heat index and wind. Statistical functions are present like zonal statistics, focal statistics. Functions related to distance and density are also there like optimal path is raster, distance accumulation. You can do band math and calculate indices like NDVI, NDSI, MNDWI, etc. We also have functions related to hydrology like fill, flow accumulation, flow direction, multidimensional functions like generate trend, predict using trend, detect change using change analysis rasters are also present. We also have image segmentation and classification functions like classify, ML classify, linear spectral unmixing, and you can also create custom algorithms using Python for image processing. Now let's see a demo in which we will go through the process of extracting coastline using multispectral imagery and band ratio technique. In this demo, we will see how coastlines can be extracted using multispectral satellite imagery. ArcGIS notebooks enable you to utilize data from ArcGIS Online or Enterprise portal with the power of ArcGIS API for Python. Traditionally, coastlines may have been manually digitized, but now with the use of continuously updated satellite imagery such as Landsat 8, we can extract the shoreline using ArcGIS Python API and even automate the process to detect changes over time. To set up a notebook, import all of the libraries that you will be using. In this case, I am using raster functions and geoanalytics functions for my analysis like extract band, stretch, convert feature to raster, clip layer, etc. We will connect to our ArcGIS Online organization and enterprise portal for getting the data for our analysis. I will begin the analysis by adding Landsat 8 satellite imagery from Living Atlas. Next, I will add buffer layer from my ArcGIS Online organization for delineating my area of interest. I will add the feature layer in map widget to determine the area for which I want to extract coastlines. In next step, we will create a data frame for feature layer which will show all the polygons inside the feature layer. In this case, I am extracting coastline for east coast. So we will use object ID equals to 2 while creating the geometry. We will use the geometry while filtering out the Landsat 8 tiles on the basis of cloud cover to get a cloud-free data. We will create a list, and using that list we will create a mosaic. The resulting mosaic looks something like this. Next we will extract bands and create single band rasters using extract band function. I have extracted 3 bands: near infrared, blue and red band. Near infrared band is selected as it is best for delineating land and water, and in the raster you can see how clearly land and water can be differentiated. Blue band is selected as water has highest reflectance in blue spectrum. And finally we will extract red band as red spectrum is highly absorbed by vegetation, and this is useful to delineate between soil and vegetation. A recent remote sensing technique to extract coastline is band ratio. In this technique, the DN value of bands are divided to generate a binary raster. I have used the following formula for creating the binary raster, and in the output raster, pixel value 1 will represent water and 0 will represent land. After applying stretch function, you can see the stark difference between land and water. For post-processing, we have used buffer layer for clipping out the extra area from the raster for minimizing the processing time. By using raster function convert raster to feature, we have converted the raster to polygon, and a data frame is created using the polygon feature layer. We will filter out the polygon with largest area, which will represent coastline. By using ArcPy function, we will convert polygon to line for better visualization. For removing noise, a negative buffer is created using the geometry of raster. After removing the extra lines, these are the extracted coastlines. In the map widget, you can see how accurately the extracted coastlines are overlapping with Landsat 8 satellite imagery. And this is how we can extract coastlines using Landsat 8 multispectral imagery and ArcGIS API for Python. Now, let's talk about global raster analysis. Global functions process products on disk by invoking imagery layer.save or generate raster functions. These functions cannot be used for dynamic image processing. These functions work on rasters including imagery layers and rasters within imagery layers. This module includes functions related to hydrology such as fill, flow accumulation, flow direction, sink, stream order, watershed. It also consists functions related to cost calculation and distance calculation. Let's do some hydrological analysis using ArcGIS API for Python and ArcGIS Pro. Now we will see how floods can be predicted using unit hydrograph. To do this analysis, I have used 30-meter digital elevation model. The workflow contains 5 major sections. First, removing noise from DEM, delineating the watershed, creating a velocity field, creating an isochrone map, and finally creating a unit hydrograph. For the analysis, we will first import the necessary libraries. For this notebook, I have imported global raster functions and raster functions such as flow direction, sink, raster calculator, slope, etc. We will connect to our enterprise portal for getting the data. For this analysis, I have taken PowerPoint feature layer and polygon feature layer showing the boundary of our study area. I have added DEM for the study area, and finally I have added a raster which represents the surface water bodies for our study area. First step for the analysis is to remove the noise from our DEM. For that, we will first create flow direction raster using the DEM. This is how flow direction raster looks like. In this raster, each pixel represents the direction in which water will flow from the pixel. After creating flow direction raster, next step is to identify the pixels with extreme values in comparison to its neighboring pixels. For that, I have used sink raster function. For better visualization, I have used stretch function on sink raster. Now you can see all the pixels with extreme values are near or inside the water bodies. Next step is to remove the noise from our DEM. For that, I have used fill function, and this is how the DEM will look like after the correction. Now next step is to delineate watershed. For that, first step is to create flow direction using the corrected DEM. This is the flow direction raster. Next, we will define the outlet for a watershed. Outlet or pour point for watershed define the end of any watershed. I have used flow accumulation global raster function for creating a raster which will show the areas where water will accumulate. Next step is to rasterize the pour point because snap pour point function requires input pour point as raster. And finally, we will create watershed using watershed function with the help of flow direction and outlet raster. This is the extracted watershed for our study area. After delineating the watershed, we will create a velocity field. For that, following equation was used. For creating a velocity field, first step is to create slope raster. For that, I have used DEM and slope raster function. This is the slope raster. Now we will create slope area term raster using flow accumulation and slope raster using raster calculator function. I have used con function to clip out the area representing watershed. This is the masked out output. And the final step is to create a velocity field. I have used item.properties function to get the parameters like maximum values, and using those values I have created a raster showing velocity. After getting the velocity raster, next step is to remove the extreme values from the output. For that I have used greater than, con and less than function. Now we will create isochrone map. For that, first we will create a weight raster using raster calculator. And again con function was used to clip the raster with the watershed. For calculating flow time, flow length function is used using flow direction and weight layer. This is the flow time raster. Now we will reclassify the flow time raster to create isochrone map, which will show a contour line that passes through points of roughly equal travel time to the outlet of watershed. For reclassifying the raster, I have used remap function. These are the intervals. I have created a data frame showing isochrone intervals and counts per class. Now we will create output showing the relationship between time and area of water flowing into the outlet. This table is used to plot the unit hydrograph. Unit hydrograph shows time taken by water to reach an outlet. It allows us to predict floods and future rainfall events. Now Kriti will show how image processing can be done using RFT class.
Thank you, Shivani. Now let's take a look at image processing using the RFT class. As we have seen earlier, raster functions can be applied to image services for fast, accurate, on-the-fly processing. A processing workflow containing one or more raster functions chained together is called a raster function template or RFT. RFTs can be created in ArcGIS Pro function editor or can be created in the raster function editor in Portal for ArcGIS. RFTs will need to be shared to your enterprise account to be able to consume them in ArcGIS API for Python. The RFT class allows users to apply RFTs for on-the-fly processing and then save the desired results to Enterprise Portal using the save function. The RFT class also has the added benefit of enabling users to automate their image processing workflows. Let's go ahead and take a look at this in action. In this demo, we will determine the site suitability for oil palm plantation in Indonesia. Proper land suitability assessment for agriculture must be carried out to determine the potentiality of a land area to result in optimum crop development and maximum productivity. We will be performing this analysis using 5 suitability factors, which are elevation, slope, conservation area buffer, soil type, and soil acidity. Taking all these factors into consideration, I have already created the RFT. Now, the next step is to publish the RFT to Enterprise Portal. Once the GIS object has been created, we can then use the add method on the Content Manager class to upload our RFT. After the RFT has been added as a portal item, we can use the RFT class to create an RFT object, which is a Pythonic representation of the raster function template. We can visualize the function chain to understand the input parameters and functions involved. In this RFT, we are using a combination of local functions, stretch, color map, and color map to RGB raster functions. A single question mark before or after the RFT object will show help relative to it. The help document will display the parameters that were marked as public by the author of the RFT. We can then assign input values to the RFT using these parameters. Now that our RFT object has been created, we will need to prepare our input layers for analysis. We can now create our hosted imagery layers on ArcGIS Enterprise from local raster datasets using the raster analysis function copy raster. Here I have given the path to the local dataset and set the raster type as raster dataset. Once the copy raster job is completed, we can see the item as well as visualize the layers of the item created. We will now need to create similar input layers for the other rasters as well. That is, conservation area buffer, slope, soil acidity, and soil type. Our RFT object and input layers are now ready. The next step is to provide these layers as inputs to the RFT object. Here we can see a preview of the output with the function chain applied on it. The green area represents land suitable for oil palm plantation. We can also persist the output to Enterprise portal using the save function on the imagery layer object and further visualize it. Next, let's take a look at orthomapping in ArcGIS API for Python. Remote sensing images like drone imagery, aerial photographs, or data from a satellite sensor will most likely be impacted by some form of geometric distortion. The shape of local terrain, the sensor angle and altitude, the motion of the sensor system, and the curvature of the Earth all make it difficult to represent three-dimensional ground features accurately in a two-dimensional map. Orthomapping is a combined process of orthorectification and mapping, in which orthorectification refers to the removal of geometric distortion introduced by the platform, sensor, and especially terrain displacement, and mapping refers to the edge matching, seamlines generation, and color balancing of multiple images to produce an orthomosaic dataset. The orthomapping module in ArcGIS API for Python can be used to generate orthomapping products like orthorectified rasters, orthomosaics, digital terrain models, and digital surface models. Below is a list of orthomapping functions supported in the orthomapping module. Let's jump into a demo and see how we can create an orthorectified raster and orthomosaic from drone imagery. Images acquired by drones are essential for creating orthomapping products. Each time an organization gathers imagery, the result is a project that includes the single-frame images gathered by the drone, any products derived from the drone-acquired images, and metadata associated with both data capture and post-flight processing. In this notebook, we will see how the orthomapping module can be used to process one such drone data. The study site used in this demo is at the Yucaipa Valley Water District in California, and the 13 drone images were taken here with a controlled route. We need to upload the images to Enterprise before they can be given as inputs to create image collection function. Camera GPS coordinates when taking each image are needed to create the image collection. This information can be stored in various image auxiliary files. For data used in this notebook, the GPS data is stored in EXIF, exchangeable image file of the images. To read this data, we will need to import the EXIF read library. In this function, we are assigning the latitude a minus sign if it is south of the equator, the longitude a minus sign if it is west of the prime meridian, and the altitude a minus sign if it is below sea level. Here we are defining a function to convert degrees, minutes, seconds to decimal degrees, and below we are utilizing the EXIF read library to get the location information of the images. These coordinates will then be used in the analysis later. The query camera info function returns a digital camera database which contains the specs of digital camera sensors from which the user can query and construct the camera properties dictionary. Another parameter required in the raster params dictionary is DEM. The DEM is required by the function to calculate the flying height information. If not set, it will use the orthomapping elevation utility service in ArcGIS Enterprise. Now that we have all the inputs ready, we can run the create image collection function and visualize the image collection created. These functions tend to run a bit long, and so for the convenience of the demo, I have already run them in advance. As we have our image collection ready, we need to compute and apply block adjustment. The compute sensor model function computes the bundle block adjustment for the image collection and applies the frame transform to the images, which is based on the raster type information we used when creating the image collection. It also generates the control points feature class, solution table, solution points feature class, and flight path feature class. The block adjustment process uses the ground control points and tie point information. A bundle adjustment computation calculates the exterior orientation for each image, such that they are consistent with neighboring images. The orientation for the whole block of images is then adjusted to fit the ground. This block adjustment process produces the best statistical fit between images and minimizes errors with the ground control. Now we need to compute the control point sets between the reference image and the mosaiced image items within the image collection. Here we are using a georeferenced data as a reference image layer in order to compute the control points. The compute control points function uses advanced image matching algorithm to find the ground control points on the reference image and its tie points on the image collection item. It requires the reference image and the image collection to have similar spatial resolution and texture for better image matching results. Now that we have added the ground control points to the image collection's control point table, let's recompute the sensor model to refine the block adjustment results. Here I have set the mode to refine and location accuracy to medium. The compute seamlines function is used to compute seamlines for overlaid images inside the image collection, usually after it has been block adjusted. Seamlines are helpful for generating the seamless mosaiced display for overlapped images in image collection. After the image collection sensor model is computed, the color correction function can be called to improve visual appearance. This is often needed for satellite data as the cross-strip images are often collected on different days with different atmospheric conditions. Once you're satisfied with the accuracy of your adjusted image, it's time to make the orthomosaic. We can create orthorectified imagery layers from the image collection using the generate orthomosaic function. The orthomosaic function lets the user choose whether or not to use the existing seamlines of the image collection for the orthomosaic imagery layer. It also has the option to choose whether or not to apply color correction settings to the output orthomosaic imagery layer. This can be set using the regen seamlines and recompute color correction parameters. And now we can visualize our orthomosaic product. Concluding this demo, we have gone through the process of creating an orthomosaic with drone imagery using the Orthomapping module. These results, that is your orthomosaic, can be used for applications in emergency response, resource management, real estate, and more. Now, I'll hand it over to Ria, who's going to be talking about multidimensional analysis, the Raster class, and the Raster collection class.
Now, let us see how we can perform multidimensional analysis using ArcGIS API for Python. First of all, let us see what a multidimensional data is. A multidimensional data represents data captured at multiple times or multiple depths or multiple heights. Using the API, we can perform complex time series analysis, height or depth trend analysis, forecasting, and regression. These methods allow you to manage your multidimensional image services, aggregate your data over time, identify anomalies, explore trends, and detect changes. Shown here are the multidimensional analysis methods that are available in the API. You can also use the temporal profile method to visualize and analyze your multidimensional dataset. Now, let us see a demo that shows multidimensional analysis using Raster module of ArcGIS API for Python. Let me give you an overview about what this demo is about. We know that one of the effects of climate change is changes in precipitation patterns. As sea surface temperature increases, these patterns changes and areas around the globe experience either an increase or decrease in their annual precipitation. Current studies indicates that the Sahara Desert is expanding due to the decreased precipitation over the region. At the same time, South America is experiencing a slight increase in precipitation in past and severe storms. Much of the world's freshwater supply is replenished through precipitation, so it is important that we understand the changes already occurring. In this brief demo, we will use multidimensional data showing monthly global precipitation from 1900 to 2017 to analyze and predict precipitation trends. We'll be taking a closer look at the Sahara Desert and Amazon rainforest regions. We have the precipitation multidimensional data published as an image service. We first create a raster object out of the URL of the image service. We can use the variable property on the raster object to get the information about the list of variables. This particular data has only one variable, and that is along the standard time dimension. In order to get the information about the dimension, we can use the getDimension attributes. As mentioned before, the data is ranging from 1900 to 2017 and has 1416 slices. There are other methods on the raster object in order to get information about the multidimensional data. As a pre-processing step, we will be aggregating the monthly data into yearly precipitation using aggregate multidimensional raster function in the ArcGIS.raster.analytics module. Here we use the mean aggregation method to aggregate the raster. We'll be also using the interval keyword option and the yearly keyword as we need to aggregate the data yearly. Once we have aggregated the raster to mean annual precipitation, we'll be using the temporal profile method to take a closer look at the Sahara Desert and Amazon rainforest region. For that, we'll first define 2 points that represent Sahara and Amazon rainforest. We'll be using these 2 points throughout this demo. In the temporal profile function, we pass in the point of interest, the dimension and the variable. We'll be also using the linear trend type. From these trend lines, we can see that the average annual precipitation in the Sahara Desert region has decreased over time. Trends in Amazon rainforest region are not much clear, but precipitation appears to have slightly increased in this region over time. We can also evaluate the changes in precipitation by detecting anomalies. A positive anomaly value indicates that the observed precipitation was greater than the long-term average precipitation, while a negative anomaly indicates that the observed precipitation was less than the long-term average precipitation. We will use generate multidimensional anomaly function to compute the anomaly for each time slice in the multidimensional precipitation raster. Since we are comparing with long-term average, we'll be using difference from mean option. And since we want to consider all slices, we'll be using the all option for calculation interval parameter. The anomaly data will let us see how the precipitation deviates from the average at each location over time. Years with positive anomaly value has more precipitation than the long-term average, and years with negative anomaly values has less precipitation than the long-term average value. We'll be again using the temporal profile. We can see that the overall trends in the Amazon rainforest region and Sahara Desert region. Over this period, annual precipitation has steadily declined in the Sahara Desert region to the point where it is now consistently below the long-term average. Annual precipitation trends in the Amazon rainforest regions are still hard to conclude, but it appears that they have slowly but steadily increased. Another way to look at the precipitation data is to use a simple regression model to look at the trend and predict future precipitation. We'll use the generate trend raster function for this. This function helps estimate the overall trend for each pixel along the standard time dimension. For this analysis, we'll use harmonic regression to account for seasonal fluctuations in the precipitation. We'll be using the symbology RFT exported from Pro to visualize the trend raster. So for that, we create an RFT object out of the RFT item and apply it to the trend raster to visualize the layer properly. We are then adding the layer to a map to visualize the layer. As you can see, the Amazon rainforest region is mostly dark purple and is experiencing an overall increase in precipitation. The Sahara Desert region is primarily green and is experiencing an overall decrease in precipitation. We can now use this trend raster to predict what the precipitation trend might look like in the future. In this case, we will use the trend raster as an input with harmonic regression to predict the precipitation from 2080 to 2027. For this, we will be using predict using trend raster function. We'll be using the dimension definition as by interval, as we want to make the prediction for an interval of dimension that is from 2018 to 2027. The interval value represents the number of steps between the dimension. Since we want the predicted value for each year, we use the interval value as 1. Also, we specify the interval units as years to predict the value for each year in the range. This new multidimensional raster contains predicted annual precipitation values from 2018 to 2027. Our predicted result shows a continued decrease in precipitation in the Sahara Desert region and a continued increase in precipitation in the Amazon rainforest region. And thus, with the simple historical precipitation data and the multidimensional analysis functions in the raster module, we were able to visualize and interpret the precipitation across the world. We were also able to predict the future precipitation. And with that, I conclude this demo. Now, let us talk about Raster Class. A raster object references a raster and can be used to query the properties of a raster dataset. Raster objects can represent web-based image services, data store rasters, and local raster datasets. To work with local raster datasets, the ArcGIS module should be available in the environment. Thus, Raster Class provides a uniform API to work with your raster data, irrespective of your raster data source. The class has more than 40 properties and 20 different methods to work with your raster data. And the class can be used with raster.functions module to apply over 170 raster functions. Next, we'll see raster collection class. Raster collection can be considered as a collection of raster objects. This collection can be easily sorted and filtered and can be used to prepare the collection for additional processing. The raster collection, similar to the raster class, can work with data store rasters, image services, and local raster datasets. This is a high-level overview of the raster collection class. It has methods for filtering, methods for calculating statistics. These methods helps in reducing the collection to a single raster based on the aggregation method used. That is, you can find the mean raster of the collection using mean statistics types and so on. There are other methods for performing analysis like the map method, which allows you to map a particular function to each item in the collection. The two multidimensional raster method to convert the collection to a multidimensional raster, etc. Now, let us see a demo that showcases raster collection class. In this demo, we'll see how we can use methods on raster and raster collection class to perform trend analysis on the time series Landsat images. The workflow would be we would be first creating a raster collection out of the time series Landsat images. We would be then performing a filter operation based on a query. We would be processing the new collection to remove cloud, shadow, etc. We would then proceed to calculate NDVI for each item in the collection. Next step would be deriving the annual maximum NDVI value. Finally, we would be performing a trend analysis and then we would be persisting the output on the enterprise. First step in this workflow would be preparing the data for the raster collection creation. As shown here, I have my data locally and I've registered this folder location as file share on the server that will be used for processing. Once the folder is registered, I can use the file share folder like any other folder, but by prefixing the keyword file shares and the file share name. We can use the list data store content function in ArcGIS.raster.analytics module to list the contents of the folder. We create a list of rasters using the metadata XML file. Also, from the names of the files, we'll be able to get the acquisition date and the names of the raster. We'll also create a list of quality rasters using Pixel QA raster for each scene. Once we have prepared these lists, we can move on to the raster collection creation part. In this step, we'll be creating a raster collection object using the raster list names, acquisition time, and quality bands list. The raster collection created has 173 items. We are now going to filter the collection from year 2000 to 2009 using the filter by calendar range methods. The new raster collection has 93 items. This shows our new raster collection. Here in this step, we are now trying to render the first raster. As you can see, we can index a raster collection. The index 0 would represent the first item in this collection. Thus, filtered RC of 0 of raster will give you the first raster. We'll be using the extract band function to extract the first three bands, and then we'll be using the stretch method to properly render the first scene. Next, we are pre-processing the collection to remove cloud, shadow, water, snow, or ice. Here, we have defined a clean function that needs to be mapped to each item in that collection. For that, we will be using the map method on the raster collection object. We should make sure that the clean method returns a dictionary in which one of the keys is raster. The cleaned RC is a new collection that has the pre-processed items. We are now trying to render the first raster of the clean raster collection. Now we need to calculate the NTVI for each item in the collection. So for that, we have defined a calculate NTVI function that calls the NTVI raster function. The calculate NTVI function is passed as a parameter to the map method on the cleaned RC collection object. As mentioned before, the function that is passed as a parameter to the map method should return a dictionary in which one of the keys is raster. By calling the map method on the collection, we would be calculating NTVI value over each item in the collection. We will now display the first raster of the raster collection that has the NTVI applied on each raster. Now, since we need to calculate the maximum NTVI value for each year, we should first convert the collection to a multidimensional raster. This can be done using the toMultidimensional raster method on the collection object. Here, we have to specify the variable field name and the dimension field name. Once we have the multidimensional raster, we call the aggregate function to calculate the maximum yearly NTVI value for standard time dimension. Now we have a multidimensional raster that has the maximum annual NTVI value. We pass that to the generate trend function to see the NTVI value trend. In this case, we'll be performing a linear trend analysis. The trend output is a multi-band raster, and the first band would represent the slope. So in order to get the first band, we call the getRasterBands method. If slope value is greater than 1, then it represents an increasing trend, and a slope value lesser than 0 represents a decreasing trend. So we are using remap function to map positive values to 1 and negative values to 0. Finally, we'll be using color map function to see how the NTVI value is actually changing. Areas of increasing trend is shown by dark green color, and area of decreasing NTVI values is shown by gray color. Finally, we'll be persisting our output to the enterprise using the save method. The image shown here summarizes the entire workflow. First step was creating the raster collection from the time series Landsat images. As a next step, we used the filter method on the raster collection to reduce the dimension of the collection. Then we perform pre-processing on the collection. We also use the map method on the raster collection to apply NTVI on each item in the collection. Then we use the toMultidimensional raster method to convert the collection to a multidimensional raster. We then used aggregate method to aggregate the raster and then calculated the annual maximum NTVI. Finally, we performed a trend analysis to see the annual maximum NTVI trend. With that, I conclude this demo. Next, I'll hand it off to Kriti, and she will be giving us a quick recap of the session before we sign off.
Thank you, Ria. So far, we have showed you a few key examples of case studies in this session, but a lot more is possible with ArcGIS API for Python. The raster module enables users to process and analyze imagery data which in turn can help make better decisions in various cases. Some examples are identifying areas at a risk of wildfires and also analyzing satellite imagery to understand the impact of wildfires and other natural or man-made disasters on the population of a region. We can also perform change analysis on data to understand the changing trends in environmental factors like sea surface temperature and precipitation. We can also process imagery to understand river water turbidity and loss of animal habitats. Farms can also be managed at a much larger scale by processing satellite or drone imagery to analyze crop health. So far, we have seen how we can process satellite and drone imagery using the functions and classes available in the raster module. Imagery and point cloud data can also be used to perform object classification and detection, pixel classification, edge detection, image translation, and more using the Learn module in ArcGIS API for Python. To know more, you can take a look at the technical session on deep learning with imagery and 3D data. Let's do a quick recap of what we have learned so far. We took a look at the functions and classes in the raster module in ArcGIS API for Python and how we can use them for image processing. Shivani showed us how we can extract coastal lines using the Landsat 8 multispectral imagery and the band ratio technique, and also how we can use unit hydrographs to predict floods. Then, we took a look at assessing land suitability for oil palm plantations and processed drone imagery to create an orthorectified image collection and orthomosaic. Ria walked us through processing multidimensional data to analyze and predict precipitation patterns caused by climate change. We then saw how to use the raster and raster collection class to perform trend analysis on time series Landsat images. If you would like to know more about the things we learned today, here are some links. On behalf of my co-presenters and myself, thank you for attending this session.